Okay. In the previous example, we have seen how to perform buckling analysis on a 1D object. Now in the next example that we are going to take, we are going to perform a buckling analysis on an assembly. Now if you see on your screen, you can see the assembly design is given over here. It is a component of a truck dumping mechanism and which is placed in compression when in service. Means when it is operating, there is a compression load acting over here, and all the components in the assembly are welded. They are all simple structures. If you can see, there's a block over here, there are some L brackets, and there is one pin rod over here which are simply welded and created. So the analysis that we have to do is we have to perform a buckling analysis on this design. The load acting on this design and the boundary conditions are mentioned over here in the image, and the material that we need to use for this assembly is structural steel. The assembly contacts that will be created in the assembly are all bonded contacts except the contact between the pin and the L brackets. Okay, so now we know what are the conditions in the assembly, we know what are the loads acting on the assemblies. So let us perform this analysis in Ansys Workbench. So we've come to the Workbench software. We will first add one static structural analysis system over here. The material that we need to use for this analysis is static structural steel, and then we will import the geometry. Now the geometry, either you can create the geometry or you can import it from any other CAD software. So let me import this geometry. So this is the geometry that we have to import. After the geometry has been imported, you can double click on the geometry cell and enter into the design modeler. Now once the geometry has been imported, you can check the models. You can see that there are 6 components over here. You can see all the components. Okay. Now after the geometry has been imported correctly, then you can exit from the design modeler and you can enter into the mechanical window. So double click on the model cell to enter into the mechanical window. So we've got the assembly into the mechanical window now. You can first check the material. Now because all the parts in this assembly are made up of structural steel, you can select them simultaneously using the control button, and then you can change the material for every component. Okay. After that, then we will have to check the connections. So we have the connections over here. So as mentioned in the PPT over here, all the contacts, all the assembly contacts are bonded except that between the pin and the L brackets. So you can see over here, the 8th region, contact region, is between the pin rod and the bracket, and we have the 5th contact region which is between the pin rod and this bracket over here. Okay. So I need to change this. I am going to allow some motion between the brackets. So I'll change this to no separation, and also contact region 8 to no separation. Once that is done, apart from this, all the other contacts will be, by default, it is going to be bonded. Okay. So now that we have changed the contact regions and the definition of contacts, after that, the next step we will perform the meshing. So let us update the meshing and perform the default meshing. So the default meshing that we get is going to be coarse. Okay, so you can see that the mesh has been performed now. Now the meshing that has been created over here is a coarse meshing. You can use the local mesh settings, the sizing option, to give a sizing for every component. You can select the component and then you can give a default element size for this. So I'll say that the element size is of 20 units. Update the meshing. Similarly, I can give another sizing for these L brackets and these strips also, plus everything. Okay, and I'll perform the so the meshing has been completed. You can see over here. So now you can observe that the meshing is quite finer and better than we got in the first attempt. After the meshing has been done, now the next part we will apply the boundary conditions. Now in the boundary conditions, we have a support at this end at the circular holes, which is going to allow the rotational motion at the holes. So for allowing the rotational motion at the holes, we will take one cylindrical support. Now this cylindrical support is going to be at these circular holes. The cylindrical support is generally used for circular objects. Let me show you that. Suppose if you have a cylindrical hole over here, and if you want to use the cylindrical support, now whenever you use a cylindrical support, you will get three connections, three options to control the motion. So we have three motions that will come. We will have the axial motion, the radial motion, and the tangential motions. So this will be the axial motion, which will be in the axial direction. We have the radial motions, which will be in this direction and in this direction. And finally, we have the tangential direction, which will control the rotational motion. Okay, so these are the three options that you will get in a cylindrical support. So now let us see. You can see that there are three options: radial, axial, and tangential. Okay. Now in this condition, I just need to allow the rotational motion. So if you see that the axial axis is the x-axis, I need to allow the rotation about the x. So that motion can be controlled by the tangential option. If you want to allow this motion, you will keep this motion to be free and the others to be fixed. So when I say this, when I select these options, it means that only the rotation about x will be allowed. Okay. After that, the next constraint that I'm going to apply is a remote displacement. Now remote displacement, when we select this option, we get all the 6 degrees of motion which we can control. And in this condition, I'm only going to allow the lateral motion for this assembly. That means I'm going to allow the motion only in x and the y direction. So this assembly can move or can translate in the x and the y direction. It cannot translate in the z direction. And the rotational motion along x. That means if the assembly is like this, if this is the assembly, we have this as y, this as z, and x is pointing towards us. So it cannot move in this direction. It cannot rotate about y, or it cannot rotate about x. So if you consider this to be x, the rotation is going to be like this. So it cannot rotate along x directions, neither it can rotate along the y direction. If you see over here, it cannot rotate about y. Okay, only rotation about z will be allowed. That means if it is rotating along z, the motion will only be in the xy plane. So this is the lateral motion that I'm going to allow for this assembly. So let us apply these constraints now. X and y is going to be free. Z translation is going to be fixed. So we will keep that as 0. Let us first select the geometry. So I'm going to select this and this over here. Okay. Then rotation about x and y both are going to be fixed. So we will keep that also as 0 degrees. So with this, now we have applied one remote displacement constraint which will only allow the motion of this assembly in the xy plane. Okay. After that, then we will apply a load. We will apply a force of 1 Newton. We will apply a force of 1 Newton in the downward direction. It is going to be a compressive load, axial compressive. And then we will solve this assembly. So let us say, so I don't need any results because I'm going to perform a buckling analysis. So the results have been captured. It has finished the analysis. After this, we will then add one linear buckling analysis to the solution of the static structural system. Once you do that, all the data gets shared. You will enter into the setup. And now in the setup, you will first give how many modes to find. Okay. And after that, we can solve this analysis. So when this analysis is getting solved, you will get the load multiplier for this analysis. Now you can see that the analysis has been done and you have got the load multiplier of 56,732 units. So that means that if I apply a force of 56,732 newtons on this design over here, this assembly is going to buckle. Okay. So with this, now we've understood how to perform a buckling analysis on an assembly.